In our last lesson for chapter 11, we're going to talk about proportional segments that happen between parallel lines. And what happens here is if we have a line that's parallel to one of the sides of a triangle and passes through the other two sides, then it divides the sides proportionally. And the converse is also true. So what does this say? If I look at this line DE, and I notice that it is parallel to AC. So these two lines are parallel to each other, and that's what it's saying right here. Then I know that the comparison of 8, which is called BD, compared to 16, which is called DA, should be the exact same comparison as 12, which we know is DE, compared to 24, which we know is EC. And those comparisons are all 1:2 ratios. Or in other words, kind of the way I like to look at it is the left side ratio comparison should be the same as the right side ratio comparison. They are both 1:2 splits. So when a parallel line is drawn to one of the sides of the triangle, it splits the other two sides into ratios that are equal to each other or congruent. In this case, in our diagram, we have a 1:2 comparison, 8 to 16, 12 to 24. The cool thing is it can happen with multiple parallel lines as well. Check this out. So from our previous slide, we had one parallel line, but now we have two parallel lines. And so if I do this, knowing from our previous lesson, we know that if I look at different things that are matching up, I know that the 21 compared to the 35 should be the same. That's the 21 and the 35 here, 21 and 35, should be the same comparison as 42 comparing to the x. So what does that mean? If I write these down, what that means is I can set up a proportion that looks like the following. I could say that from my highlighted colors right now, that 21 divided by 35, sorry for the bright green, should be the same comparison as 42 compared to x. And then we do the cross multiply. I don't know if you remember from a couple slides previous. So I'm going to multiply my 21 times x, and I'm also going to multiply my 35 times 42, and so that gives me my 21x should be the same thing as 1,470, which is what I get when I multiply 35 and 42. And of course you would divide both sides by 21, and then you find out that x has to be 70. So this is the way that you would find the x. We actually learned that in the last slide because we were talking about this triangle right here, which was one triangle that had a parallel line cut through it. But we can also find out the y value as well, because what we can do is we can use the same idea with other pieces that are chopped up. So now I'm going to highlight a couple more pieces, and I'll show you what I mean by that. So down below now, I'm going to have the 28 in pink, and I'm going to have the y, I think, in, well, what color would I like here? I like blue, dark blue, no. I think I'm going to do gray. So now, we just got done with the comparisons of the 21 to the 35 and the 42 to the x. But now what I'm going to show you is that instead, if I want, I can do 21 compared to 28 is the same as 42 compared to the y. And so if I write that out color-coded, what I would see is 21 over 28 should be the same comparison as 42 over y. And then when we cross multiply, of course, you would see that you would get, in the cross multiplying, if I took my 21 times y, that would give me 21y. And then I could take my 42 times 28, and 42 times 28 is 1176. And when I divide both sides by 21, I find out that my y in the end turns out to be 56. So this idea of parallel lines works whether or not it's one parallel line or multiple parallel lines. It splits the triangle into ratios that are congruent. And so that's called a proportion. You can solve them just like we've done here in the last two examples.